In 1926, Erwin Schrödinger wrote down an equation that would change physics forever. It described how quantum particles move, how they evolve, how they are. And he hated it. He hated his own equation because there was one symbol in it he couldn't stand. Right at the front, I, the square root of -1, a number that by definition cannot exist. You cannot take a square root of a negative number, or at least you cannot point to anything in the physical world that gives you negative when squared. Schrödinger knew this, and he called his own equation crude. He hoped that someone would replace it with something entirely real. And nobody did, not for a century. And then in 2021, a team of physicists designed an experiment. They said, we can test it. We can settle whether imaginary numbers are actually necessary for quantum mechanics or just a convenient shorthand. They ran the experiment and the result was clear. The imaginary numbers won. Complex numbers, they declared, are fundamental to reality, not optional. It's baked in. Case closed, right? That's what everyone thought. Until this year. A team in Germany re-examined the mathematics behind 2021 proof, and they found something. A hidden assumption, a postulate that didn't have to be there. And when they replaced it with a different physically motivated rule, quantum mechanics worked perfectly. No I required. Now, before we understand why this matters, we have to understand what imaginary numbers even are and how they got into physics in the first place. Imaginary numbers, the name alone, who gave them that? René Descartes in 1637. He was solving cubic equations and he kept running into solutions that involved square roots of negative numbers. He called them imaginary as an insult. They weren't real quantities. They couldn't be. There is no number that you can multiply by itself to get a -1. He named them in a way that ensured nobody would take them seriously for 200 years. And yet, they kept showing up. In geometry, in optics, in equations that describes waves. It turns out multiplying by I does something very specific and very real. It rotates something by 90 degrees. So I isn't a number in the usual sense. It's a rotation operator. A complex number, something like a plus b into I, is just a way of describing a physical point in two-dimensional plane. The real part is horizontal. The imaginary part is vertical. Multiplying by I rotates you by 90 degrees. And that's actually kind of elegant. But why does quantum mechanics need rotation? Because quantum particles behave like waves. And waves have two essential properties. Amplitude, how tall the wave is, and phase, where the wave is in its cycle. Two waves can combine. If their phases align, you get a bigger wave. If they are opposite, they cancel completely. Complex numbers capture both pieces in one neat package. The amplitude is the distance from the origin. The phase is the angle. So when Schrödinger needed to write an equation describing the wave function, the mathematical object that represents every possible state of a quantum particle, complex numbers were the natural language. Natural, but Schrödinger still didn't like it. He didn't like it because the wave function itself is never measured. When you actually detect a particle, you always get a real number. Position, momentum, energy, always real. But I lives entirely in unobservable mathematics. It's like having a blueprint for a house that's drawn in a color of ink that nobody can see. So, for decades, physicists just accepted this. An invisible number running the entire show. And they did more than just accept it. They built an entire edifice on it. The Schrödinger equation became the law of motion for the quantum world. And every measurement ever made matched its prediction to astonishing precision. If I was a crutch, it was the most reliable crutch in scientific history. But someone finally decided to kick it. In 2021, a team led by Marc-Olivier Renaud and Nicolas Gizan asked a question nobody had properly asked before. Not, is I convenient? Obviously it is, but is I necessary? Can we construct a version of quantum mechanics using only real numbers that makes all the same predictions as the standard complex numbered version? They designed a bell test. You have heard bell test. They are how we prove quantum entanglement is real. Two entangled particles, two observers, Alice and Bob, they measure their particles and compare notes. The correlations between their measurements are stronger than any classical theory allows. Standard quantum mechanics. But what did they change? They added a third person, Charlie, and crucially, they used two separate sources for entangled particles. Alice gets a particle from the first source, Charlie gets one from the second source, and Bob gets one from each source. Bob does something called entanglement swapping, a quantum operation that links his two particles. When this works, Alice and Charlie's particles become entangled, even though they never came from the same source and never interacted. Now here's the key. Renault and Gizan calculated what maximum possible correlation between Alice and Charlie's measurement would be in a purely real numbered version of quantum mechanics. Then they calculated the maximum in the standard complex version. They were different. The real valued theory had a ceiling. The complex valued theory reached higher. So the experiment was simple. Build the setup, measure the correlation, and see which ceiling the result breaks through. The results broke through the real number ceilings by a lot. A team at the University of Science and Technology of China in Hefei built the experiment. The correlations they observed was far exceeded than maximum allowed by any real number formulation. It seemed definitive. Complex numbers were not just a convenience, they were a requirement of nature. Now, Nature, the magazine, published the paper, and it was a big deal. Science YouTubers made videos about it. Imaginary numbers are real. Quantum mechanics proves I exist. Tens of millions of views across dozens of channels. The story was clean. The experiment was conclusive. The philosophy was mind-bending. And it was all wrong. The experiment worked perfectly. What was wrong was the assumption about what the experiment was testing. Here is the hidden assumption. When you add two quantum systems, say Alice's particle and Charlie's particle, and you want to describe them as one combined system, you have to use a mathematical operation called tensor product. The tensor product is how you stitch quantum states together, and this is where the problem lives. Renault and Gizan assumed, reasonably because it's standard thing everyone does, that a real valued version of quantum mechanics would use the same tensor product, the same stitching rule, but that's not necessarily true. Think about geometry. If you're drawing triangles on a flat piece of paper, the Pythagorean theorem works. A square plus b square equals c square every time. But if you draw a triangle on a surface of a sphere, on a curved surface, that rule breaks. The hypotenuse is different. So the rule of combining things depends on the space you are in. The tensor product that works for a complex quantum mechanics might not be the right one for real quantum mechanics. Dagmar Bruss and Pedro Barrios-Hitter at University of Düsseldorf, along with collaborators Anton Trushkin, Hermann Kamperman, and Michael Epping, went back to 2021 paper Postulate. They found that one particular postulate about how composite systems are formalized was unnecessarily restrictive. When they replaced it with physically motivated alternative, a different rule for combining systems, the real number theory produced identical predictions to complex numbered one. Identical, meaning there is no experiment, not even the fancy 3-person bell test that can tell them apart. The 2021 experiment didn't prove that complex numbers are necessary. It proved that if you force the real valued theory to use the complex valued theory's combination rules, it breaks. Which, yeah, of course it does. It gets better. Two groups reached the same conclusion independently. Timothy Hofferman and Mishka Woods in France published their own real-valued formulation, and Craig Gidney at Google Quantum AI came at it from entirely different direction: quantum computing. In quantum computing, there is something called as T-gate. It's the one operation that requires complex numbers to describe its rotation quantum bit state around the complex plane. Every other gate can be described with real numbers. Gidney proved that you can eliminate T-gates from any quantum algorithm by preparing a special phase gradient state beforehand and distributing copies of it. Yeah, what does this mean? It means that it's a mathematical proof that quantum computing does not need complex numbers either. Three groups, three different approaches, all arriving at the same place. Complex numbers are a matter of convenience, not necessity. Now, before we get carried away, none of this changes quantum mechanics. The experiment still works. The predictions are the same. Nobody is throwing out their complex numbered textbooks. In fact, the real valued formulations are ugly, extremely ugly. In 1960, a Swiss physicist named Ernst Strugelberg developed a real valued quantum mechanics. For a single particle, the complex wave function uses one complex number, which was two real numbers. Strugelberg's real formulation needed 4. For two particles, the standard theory uses 4 complex numbers, and Strugelberg's needed 16 real numbers. It exploded. So you can't do it without I, it just makes everything far worse. The modern formulations are more elegant than Strugelberg's, but the point stands. Complex numbers are the natural language of quantum mechanics. Even if they're not the fundamental requirement, Schrödinger gravitated toward them because they were, in his own words, extraordinarily much simpler for computational purposes. Even the researchers who proved I isn't necessary admit that complex numbers still feel like the right tool. Which raises a question. If a formulation is vastly simpler and more natural, and the universe seems to use it, does it matter that an alternative formulation exists? That's the philosophical heart of this. Some physicists like Vlatko Wittrol of Oxford point out that even the real valued theories retain the hallmark of complex numbered arithmetic. They don't contain I explicitly, but they still multiply things exactly as though they were complex numbers. The structure survives, the rotation survives. So you're not really getting rid of I, you're just hiding it in a more complicated set of rules. Or, this is the deeper reading, maybe what we call the complex numbers was never about I at all. Maybe it was always about rotation, about phase, about the fact that quantum states live on two-dimensional plane and need two numbers to be described. The symbol I is just the notation we invented for the 90-degree rotation on that plane. You can rename it, you can encode it differently, but the geometry doesn't go away. The rotation was real the whole time. The I was just pointing at it. For 100 years, physicists believed a mathematical object that Descartes named as an insert imaginary was fundamental to the fabric of reality. And in 2021, we thought we proved it. And now, it turns out the experiment tested was wrong thing. Or rather, it tested the right thing under the wrong assumption about what rules a real number theory was allowed to use. So what actually is fundamental? Can I be removed? That's the question that should keep you up at night. The Schrödinger equation contains I. The Dirac equation contains I. The standard model contains I. And if I is just a mathematical convenience, if it's a notation for rotation, not a feature of reality, what else in those equations is just notation? The entire mathematical structure of quantum mechanics might be, in some sense, optional. We don't know what's fundamental and what's just language we choose to describe it. The equations work, the predictions are flawless, but when you look at the symbols on the page, you can't tell which ones are pointing at something real and which ones are just the ink color we happen to pick. Jill North, a philosopher of physics in Rutgers, put it in this way: the mathematical formulation does guide what we infer about the nature of the physical world. When the mathematics changes, even in ways we don't change any experiment predictions, it changes what we think reality is. So Descartes named them imaginary, and we have been fighting about whether they are real ever since. The honest answer is, we still don't know. But here's what changed. Before 2026, the answer seemed to be yes, I is fundamental. The experiment proved it. Now the answer is maybe, or maybe not. And maybe that's the most profound thing of all. You can't remove the central symbol from a central equation of quantum mechanics, a symbol Schrödinger himself wished he could erase, and the physics doesn't even care. The numbers Descartes called imaginary have been running the universe for a century, and now we know they were never running it, they were just describing it. The question is, what else is just